love that I work in a field that was founded by a woman. Maths. I'm British, I said maths, not math.
Maths.
So when it points at you, you see it, but then it rotates away and you see nothing until it makes a whole rotation. I love that she knew her instrument well enough to see this thing and be like, no, this is real. And someone went, no, that's not real. And she went, yes, it is, I'm gonna prove it.
You said this discovery would break physics. What did you mean when you said that? Welcome to Season 1 of No Credit, the video podcast that highlights the voices and stories of women and gender diverse innovators in STEM across various backgrounds and eras to ensure that their contributions never get left out of history books. Hi, I'm Zeynep Güler-Tak, Z for short, coming to you from the unceded territories of the Musqueam, Tsleil-Waututh, and Squamish nations here in Vancouver, British Columbia in Canada. This season specifically, we're focusing on the local storytellers and STEM professionals working here in Vancouver, BC. I'm very excited. So just to let you know, each episode we'll get to chat with these amazing professionals, these really cool people, and really ask them what it's like to innovate in the city. And how they're bringing in their community and how they're bringing in everything that they've come with through their journeys into their work, into their contributions, into everything that they are doing to shape our future. Because they're doing some incredible things. Teaser. By the end of each episode, we'll uncover whether their legacies of histories and amazing pioneers were impactful or all in vain. So I'm going to check in with you at the end of each episode and you be the judge. This episode we're inspired by one of the scientists who took us to new heights with physics and astronomy through the discovery of pulsars, Dame Jocelyn Bell Burnell. Almost like cosmic clocks, pulsars help measure ripples in space and time, which Einstein had predicted. Despite Bell Burnell's pivotal role in the breakthrough, she received no credit, and the 1974 Nobel Prize for Physics was awarded to her male supervisor. Following that omission, she became a staunch advocate for women in the field. In Vancouver, our very own trailblazer from the University of British Columbia's Physics and Astronomy Department, PhD candidate Kathryn Crowter, is joining us for this first season of No Credit. Thanks for having us and thanks for being here.
Thanks for having me.
Yay.
This is very exciting.
Yay! It is exciting. I agree. I'm there with you. And I'm gonna be referring to my notes because I gotta be on task here. There's very important things we have to talk about. So first, the most important thing that I need to know before all of this, what is your favorite snack that you don't share with anybody?
Most form of sweets, yeah.
So like anything, we're talking muffins, we're talking like sugar candy.
Yeah, like I absolutely bought a packet of Tang Fastics yesterday and ate all of them.
You say those thingies that
the Haribo Tang Fastic things.
Oh my gosh. Okay, so so candy, sweets, all of the goods. It's all in your realm and you don't want to share it with anybody.
No.
Nobody gets it. Nobody gets it. All right. Sorry, viewers, we're not going to share. Now, we did talk about, you and I, when we were chatting prior to this, we did talk, and you were very excited that we were mentioning Dame Jocelyn Bell Burnell. So tell me a little bit about her legacy. Tell me about how she has impacted you, your work, and how you know about her, really.
Well, I mean, I love that I work in a field that was founded by a woman. I love that she knew her instrument well enough to see this thing and be like, no, this is real.
Right.
And someone went, no, that's not real. And she went, yes, it is, I'm gonna prove it.
Right.
And then, she discovered pulsars and the Nobel Prize for discovering pulsars went to not her.
Right.
Right? Which is just very emblematic of the time.
Yeah.
And yeah.
Exactly.
She didn't get awarded many things after it to be like, oops.
Well, there was an oops, right? It usually happens with an oops afterwards.
Yeah.
But the realization beforehand wasn't there.
Right.
Okay, and that's the field for you, right?
Yep, it's better now, but still.
Still sucks, right? Okay, so let's talk about your journey.
Yes.
because, so your journey through space and time, how did we get here today? Tell me about some of the kind of smooth sailing, but also some of the rough waters. We're going to continue with this boat metaphor. I can't help myself with the ripples and the flows and the movement. So, so please bear with me, and please I'd love to hear a little bit about how you got here.
Well, like, okay, I've always been good at maths. I'm British, I said maths, not math.
Maths. Got it.
I like it. I like the flow of logic.
Yeah.
I happened to go to a girls' school, which I think helped me avoid a bunch of the early sexism that a bunch of other women I know hit, right? And yeah, had very supportive parents. I was able to go to university, and they're like, yeah, you can do anything, go do it.
Okay, okay, so that helped tremendously.
Definitely.
Okay.
I mean, I think if my ambition had been, I want to become a singer, there would have been a different conversation about, okay, what's your backup plan, really? But
so they were cool with the science. They were definitely interested in the math and science of it all.
100%.
Okay, so could it have been lawyer or anything and they would have been okay, but it's definitely the arts. They were like, no way.
Yeah, very pro logic.
Okay,
like,
that's fair.
This seems dubious.
Okay, so they were helping kind of nurture this path. They were like, please stay on that path. Please, let's hope Kathryn stays. Okay, okay. And then as you progressed?
Yeah, then, I mean, I didn't grow up, I like looking at the stars, but I didn't grow up looking through a telescope.
Right.
Right? I was kind of like, yeah, they're pretty, but
It's all right.
The universe, it's fine, I guess. Yeah, but like, what I love about astro is that you bring in all these different parts of physics.
Yeah.
Like, to understand a star, you have to know about gravity. There's fluid, like all this motion in there. You have to know about fluid dynamics. It gives off radiation. You need electromagnetism. There's weird particle interactions. You got particle physics.
That's right.
You like pull in things from all over the place, and you also get like the most extreme objects that exist.
Okay, tell me, extreme. This is very dramatic here.
So dramatic.
Extreme, what are we talking about here?
So like, black holes are the densest thing in the universe. Like, you cannot manufacture a supermassive black hole in a lab. Right. I mean, it would destroy the lab and the whole solar system.
So
slight issue.
Big reason why we don't, yeah.
Or like neutron stars, second densest thing in the universe.
Right.
Hundreds of thousands times higher magnetic fields than the highest we've ever managed to create here, with explosions and weird things like that. It's pretty cool. That
is pretty cool. Okay. I don't want to backtrack. I don't want to like get off course. I could ask you probably 10 more questions about this because it's so dramatic and we're so dramatic. So, okay, let's continue along. So this was kind of where you kind of got excited about this.
Yeah, so I knew I wanted to continue learning. Right. I went to university. Yeah. I love asking why, figuring out why something works, how it works.
Sure.
So I was just kind of looking for what I wanted to ask why about. Right. So I hit on astro, and I was looking to leave the UK, go somewhere else. Well, you know, I could and didn't have a partner and had the freedom to do that.
Freedom, woo!
And I ended up in Vancouver because I picked UBC off like a top 50 list.
What?
Yeah, I googled like best places to do grad school for physics or astronomy, and I was considering UBC and I think Japan. Similar, right?
It could have been, right? It could have been either. You were going to go that way anyway, right? Okay.
And then, I mean, UBC, I get to live in Vancouver, and it's gorgeous. I still grin like an idiot on bus rides because you can see the mountains and the sea.
Same.
It is ridiculous.
Bananas. I know. It's like heaven on earth for sure. Yeah.
Like, this is a legitimate holiday destination where I live in.
I know, right?
What?
What's happening? What? Okay, so then you were like, I'm in it to win it. Going to Vancouver.
Yeah.
Okay.
And then transitioning from like undergrad to grad school is interesting.
Right.
Because in undergrad, you have all the answers, right? There is a solution to everything. Grad school is like, we don't know, work it out. You're like, wait, what now?
Okay, so that was a shocker for you. You're like,
that's a bit of a shock.
Okay.
But yeah, that's pretty good. And like, all right, it is a very male-dominated environment.
Yes.
Astro a bit less than the rest of physics.
Sure.
But definitely in my undergrad, like about a third of us were female, and then it went to a quarter. So just kind of used to that environment and continue it. You don't really notice until you go somewhere else.
Interesting.
Like I TA'd, I did a TA and it happened to be in like, I don't remember, the social sciences building or something. And just like walking through that building, like, oh, there's a lot of women here.
There we go. So you like, did notice.
Oh, wait.
Wait a minute. I don't. Okay, so that's when you did notice. And we're going to get to that a little bit in a second. And now, okay, so take us a little bit closer to where we are now. And if you want it, and then I have a big question about obviously this one research breakthrough or project that you've been working on, but kind of take us to where we are now.
Yeah, so I was doing my master's. I got a concussion. Apparently brains are important for sciencing.
Right, that's your instrument.
Very much so. Yeah. So I was off for a while. It took me a while to get my brain back. That was a question mark for a while.
Sure, sure.
And then thankfully, I had a very supporting supervisor. Like, I know someone who got a concussion and 2 weeks later, their supervisor's like, why aren't you back in the lab?
Oh my gosh. Okay, so your supervisor was definitely helpful
absolutely lovely about it. And luckily, I did recover enough to be able to, you know, do very intense science.
Right, so you recovered enough to get back to it.
Yeah, and decided to do my PhD. And and so here I am now. There's a thesis between me and graduating.
Oh my God. Okay, so thesis, very exciting. We're on the edge of our seats right now. Recently, you and over 200 scientists across the world did something very, very exciting. You really pushed the boundaries and uncovered new insights into Einstein's theory of relativity, which is bananas to me and to our viewers, I'm sure. You said this discovery would break physics, right? What did you mean when you said that?
So it doesn't break physics yet, but we want to. Right? Like every time you see something odd or something that doesn't fit into the paradigm, right? You discover something really new and interesting. Like, hey, this shouldn't exist. Why does it?
Right.
Oh, look, we have to invent quantum mechanics.
Right. Okay, cool.
Right? So like this is how we learn as a species and progress is like, oh, we find something that doesn't fit our current model of the universe. It breaks what we know. Okay, let's build something new.
And in your case, breaking is a good thing.
Yes.
Right?
As long as it's not a telescope.
Oh, please don't break those telescopes, right? Or you're not like, oh, I broke a wine glass or a tea glass. No, we don't like those breaking.
No.
But we do like breaking science and technology and all that because we're finding new ways of doing things.
Absolutely.
Did you hear that? Breaking is okay. On this podcast, we're okay with breaking things. Okay, so then this brings me to, what are you working on now? Please tell me. I'd love to hear everything because obviously you're talking about you're one thesis away, but then I think we had mentioned a few, you and I were chatting and you were telling me about some of the exciting things you're working on. So I'd love to hear about them.
Yeah, so you mentioned these cosmic clocks, right? Yeah. That we use to...
Which is such a cool term. Like,
I know,
are you kidding me?
First you came up with that was great.
Right? Tattoo that, right? Like a cosmic clock.
Oh, absolutely.
Like, what does a cosmic clock look like, right? Yeah.
So we see these pulses of radiation from them really regularly.
Yeah.
And they're useful for all sorts of things.
Yeah.
Testing general relativity, detecting gravitational waves, seeing if new weird particles exist.
That's
also.
it.
Like a bunch of they're actually very useful objects. It's like physicists dream, these things exist.
Right.
And so I'm trying to find more of them using a radio telescope called CHIME, which is near Penticton.
CHIME.
Yes.
Okay.
Astronomers love acronyms.
Yes, I figured that. I was like, CHIME is like a really simple word. This is not normal. Okay, so what is it?
So it stands for the Canadian Hydrogen Intensity Mapping Experiment.
Okay.
This is why we call it chime.
I think I'm going to stick with chime for sure. Okay, so this is a telescope.
Yeah.
And it maps.
Yeah, so it's a radio telescope.
Yeah.
And what it's really cool. I'm biased, but it's really cool.
It's fair. It is really cool.
So it's originally a cosmology experiment.
Yeah.
Trying to look for hydrogen in the early universe and use that to model how the universe kind of evolved and developed.
Okay.
The cool thing is, it's weird.
It should be.
Yeah. Picture a telescope.
Okay, I'm picturing it
I'm guessing you have like a dish and a thing.
Yeah.
Yeah, that's not what it looks like.
What are you doing? You're breaking my idea of it. Okay, so.
Breaking it's good.
Right.
So it looks like 4 half pipes.
Right.
Like about 20 meters across and then 80 meters, 100 meters long.
Sure.
4 of them next to each other.
Okay.
So it doesn't move. It just looks at the sky that's above it at that point in time.
Okay.
And then the sky turns.
So it's kind of like a cross section of the sky that it's looking
You get
at?
this strip of the sky right above you. And then the sky turns over it. So you can see what's ever in the strip at that point in time.
Got it.
But because it doesn't move, it lets you hook up various experiments to it that all use the same data.
Got it.
So normally, if someone's like, I'm like, oh, hey, I want to go look at this cool pulsar, I have to apply for that time, and someone else can't use the telescope while I'm pointing it at this pulsar.
Oh.
Whereas because we have no choice about what we see, we can hook up a bunch of other stuff to it.
That's cool.
So there's the original cosmology experiment, there's one that looks for these weird things called fast radio bursts, and there's one looking at pulsars at the same time. So I'm trying to use it to discover new pulsars.
And then when we discover those new pulsars, are we naming them funny names?
Oh, no.
What are we doing with them?
I want a pulsar called Fred so much.
Okay. I think I do too. I like that name.
So, like, yeah.
Perfect. One syllable. Awesome.
Alas, pulsars get named after where they are in the sky.
Got it.
So they have fun names like J2256 minus 1024.
Yeah, no, Fred. Fred. I'm sticking with Fred. Okay, so we're looking for Fred.
Yes.
Okay, and then when we find Fred, what are we going to discover? What will this help us with?
So, I mean, the dream object at the moment is a pulsar and a black hole orbiting each other.
Oh, gosh. Okay. Give me the goods on what that means for us.
So, it's a really extreme gravitational environment.
Drama.
So, I know.
Right. Okay, so the drama's there. Okay.
So the signal from the pulsar has to travel past the black hole.
Yeah.
Like if it's edge on anyway. Yeah. And the black hole stretches space-time. And so when it's going past the black hole, you get a delay. And when the black holes, they rotate, and it's not in front of it anymore, the delay is gone.
Got it.
So that is one of the things that lets you test general relativity, for example.
So we want to test more of relativity.
It's going to break at some point.
Yeah, okay, so you're trying to break it. We just now, breaking news, breaking the theory of relativity is on it's on your slate.
We know that at some point general relativity does break down. It doesn't work in really small scales where quantum comes in.
Got it.
So it's not like we're pretty sure we know everything.
Right.
We know that there is something left to discover. The question is, does it still work as expected on really large scales? And that's one of the things this can help with.
Oh, see, this is dramatic stuff. And it's stuff that you want to break theories from previous scientists.
Absolutely.
To take us forward.
The famous quote, standing on the shoulders of giants, right?
That's it. So, Kathryn, I could have sworn I learned about black holes, pulsars, theory of relativity in high school, but I don't think I was paying proper attention.
That's fair.
So I would really love for you to give myself and our viewers a little bit of a refresher, if you don't mind.
Totally.
Yes, my favorite part. Okay, so I would love to do kind of like a wrap. This is kind of rapid fire as well, but we're just, throwing stuff at you. Let's start with, what are pulsars?
Yeah, no worries. I mean, when I got to grad school, there's so many words, right? Quasars, blazars, pulsars. I mixed them all up. I don't anymore.
I'm not the only one. Okay, good.
So a pulsar is a neutron star that's spinning, and neutron stars are ridiculous. Take 1.5 times the mass of our sun, squish it into the size of a city, 15 kilometers across, and then rotate it really fast. because it went from being something huge to being something small.
Right.
So, it had a bit of rotation beforehand.
Yeah.
And exactly like a figure skater, if you bring your arms in, you get faster.
Analogies. Okay, so figure skating analogy. Do you think this is the moment to bring in our prop? This is Santiago. This is
the
our
pulsar.
Okay, so can you give us a demo of kind of how it moves?
Yeah. So, okay, this is the neutron star, super dense thing. It's spinning. I have a fun fact later.
All these fun facts are coming all at once.
It has a magnetic field.
Right.
So it's always on, right? The thing itself doesn't pulse. It's just that we don't see it all the time. So it's kind of giving off radiation. So it's a pulse. If you can see the word pulse, you see the radiation or a pulsar, right? If you don't see it, you can't. So when it points at you, you see it. But then it rotates away and you see nothing until it makes a whole rotation and comes back again. And you see the pulse again.
Pulse.
Pulse and then nothing, and then a pulse and then nothing.
That's it.
Yeah.
So
this is a pulsar.
the magic of our pulsars.
Yeah.
All right. And so how do these relate to, thank you, Santiago, very helpful. How do these relate to black holes?
So super useful, basically. You can use them because you see a pulse every rotation.
Yeah.
And they're really dense and a bunch of them rotate really fast. Like, pulsar fun fact.
Fun fact.
So your blender, I spent a while Googling blenders. The fastest one I found, the blades make one rotation 30,000 times in a minute.
No.
Yeah, right? The fastest pulsar, 43,000 times in a minute.
Okay.
Like 1.5 times the sun, squished into the size of a city, spinning faster than a blender.
Yeah, no.
That's ridiculous.
That is bananas. Yeah.
Science.
Yeah. Science.
Space.
Space. Science. Okay, so then, the black holes.
Right, so you can use that, right? It's kind of like a metronome, this really quick tick you can use to measure things.
Ah, there's the cosmic clocks part.
Indeed,
Got it.
cosmic clocks.
Got it.
So if you want to measure gravitational waves, right, space-time itself, you're squishing and stretching, good way to do that is with these astronomical clocks.
Right.
You can see the pulses start to arrive like a bit later because space has been stretched, or a bit earlier when it's been squished. So kind of this gift from the universe that let us measure these gravitational waves, which emanate from supermassive black holes and stuff in the middle of galaxies, which is very cool.
You just took us all the way out there and back. I appreciate that. So as you stand on the shoulders of giants, what are some of the detours that you felt that you would have faced? Because you did mention you had an accident. You did mention that you noticed there was the lack of your kind in your program. What are some of the detours that you found that you really were able to kind of, because they're detours, you're still going back on track. What were some of the things that you can share with us?
So I think I've been pretty lucky thus far as sexism goes. It's the odd, weird thing. Like, you notice someone always starts explaining to you further back than they do, like, their male colleagues.
Oh, yeah.
It's
That's
like
so
a
subtle.
weird, consistent pattern.
Yeah.
And you're like, okay, you're probably not aware of that, but you're doing it. There's more overt stuff, like when you're a teaching assistant, you get feedback from the students and, like, Willem told me to wear skirts more often, right?
Oh, okay. Yeah. Very overt. Yeah. Okay. Did they tell you to smile more too? Because honestly, yeah, exactly.
Everyone has, right?
We have been, yes.
But yeah, I'm also pretty lucky. Like, the only unprivileged things about me are that I'm female and I'm queer, right? Yeah. And I'm kind of straight passing.
Right.
So, and my supervisor is a woman, which, I find very inspiring.
Absolutely. Are you kidding?
Yeah.
And this is the supervisor that was understanding and helped you through the, okay.
Ingrid Stepp, I wonder.
Okay. Shout out. Okay, so that you have been through detours, and it's really important to explain that this is kind of what are some of the ways that the field is being shaped as we speak. So what would be something you wanted women and gender diverse people to know about the STEM fields right now? Kind of your message, you know?
My message, oh no.
No pressure whatsoever to break anything. Yeah.
It is changing. We need to change it more.
Right.
And I think the most important thing is that you are valuable, right?
Yeah.
It's there are so many studies showing if you have a more diverse group of people working on a problem, they come up with more solutions and original things, right? Like we want different ways of thinking, different ways of approaching a problem to get anywhere.
That's it.
It's easy to feel like you aren't valuable or you're all alone, right? But your contribution really is. Yeah, I think that would be what I would say.
Okay, I like that. And then what would you tell your 10-year-old self right now? Because you were interested in this later on, it sounds like, right?
Yeah.
You weren't quite sure what you were really interested in until you really got into it. So when you were 10, you're looking back at your 10-year-old self, what's that kind of message or what's that kind of advice or words of encouragement?
I would say stay curious, right? Like keep asking questions. And be okay with being wrong. All right, I had trouble with that when I was 10.
At 10, you were like, I don't like being wrong.
You're like, I am right. I will invent reasons why I'm right.
Okay.
But I mean, being wrong is a great skill.
Yep.
And it's good in science to admit you don't know things.
That's it.
Right? That's how you learn stuff and contribute rather than being silent in fear in a meeting.
That's it.
So yeah, stay curious, be okay with being wrong, keep asking questions.
I like that.
Yeah. Right, so my favorite pulsar fact is that, so if you squish every human on Earth, it's really morbid, that's why I love it. If you squish us all into the size of half a sugar cube, that's about how dense a neutron star is.
This old guy, Einstein, and his theory of relativity, I mean, we all have heard it a million times, but if you had to pull it down to us, bring us back from the universe to right here, could you describe the theory of relativity?
So, general relativity is really cool. It's the idea that space-time itself gets distorted by mass, but then how space-time is curved and distorted also tells mass how to move. So it's this like dance between two things, right? You have like, you picture a rubber sheet and you drop a ball in it, it bends. That's kind of space-time distorting. Yeah. But if you flick a marble, it's gonna go around the funnel. That's the space-time distortion telling matter how to move. So it's this interplay between these two things that is really cool.
Okay, so when you're referring to mass, so we're going to talk about ripple, or how you distort space and time, which is blowing my mind right now.
It's hard to visualize.
I'm like, oh my gosh. What is that what could that matter be that could be dipping in and creating that mass ripple?
So like, you're matter, I'm matter, the Earth is matter. Yes. Gravity is super, super, super weak. Yeah. It's weaker even than the weak force, which I find quite amusing.
Yeah.
But so you need something big, like the sun, to have a real effect. Right. But you know, the Earth has its own has mass. Yep. It makes a distortion. That's why the moon orbits us, right? Or satellites we can put around that. But you need something planet moon-sized plus to be able to have something decent.
Interesting. Yeah. All right, we're getting there. And then finally, what do you want people to know about your work?
I think that there is more out there to discover. It's interesting, it's weird, extreme, and it's one of those things you ask like, okay, but what is the point of studying this?
Sure.
And it's like training people in tech, right? Yeah. But at its core, it's like to discover things, right? Knowing stuff about the universe, finding new theories of physics always ends up benefiting us in the future. But most people who do it aren't doing it for that reason. Right. We're doing it because we want to keep asking why and find out what's going on.
That's it. Thank you so much, Kathryn, for having us and for being here. And I feel smarter. I feel more empowered to go open up a physics book from high school. I still have one in my like keepsakes drawer. And I feel closer to you, so I appreciate you telling us your story and sharing everything with us and inspiring the heck out of us. We learned about the legacy of Dame Jocelyn Bell Burnell and how it's come to life through the work that you get to do, and pulsars, and kind of which led to the theory of relativity and everything that we love so much about the world and physics and everything like that, and the universe. So the main takeaway for me is, I mean, I loved when you described bending, like, and the ripples in space and time. That is probably the coolest thing in my brain that I can't get out of my brain, that it ripples almost like, and it changes and defines how movement works around it. So that's cool. That was bananas. I mean, I'm sure you'll take a lot from this. That's what I'm really taking and I'm thinking about right now. So I appreciate you. Thank you for your story, and thanks for sharing everything with us. I do want to ask the big question. I promised I would at the end. Do you feel like Dame Jocelyn Bell Burnell's legacy was impactful, or was it all in vain?
Absolutely impactful. I think it's a wonderful thing to work in a field that was founded by her.
I think so
And
too.
a great reminder of the cautionary tale too. It's like, who are you not giving credit to? Like, who really did the thing?
On that note, when we talk about credit, I want you, our viewers, to let us know what you think. Do you think that Dame Jocelyn Bell Burnell's and some of the amazing women and gender diverse scientists and tech people in this field, were their legacies impactful or all in vain? You got to tell me. Thanks for tuning in to No Credit. We hope you've enjoyed hearing about the incredible stories of trailblazers in the STEM and creative fields. Together, we've challenged stereotypes and ensured their groundbreaking contributions are never left out of history books. Until next time.
This is very, okay, good for her. We landed on a space rock. Like, hello.
So when it points at you, you see it, but then it rotates away and you see nothing.
Hers were the first ones specifically designed to power this machine and take it kind of beyond basic calculator status into a computer.
And so I just think of like all of the indirect impact it's having, and I just can't think of anything cooler.
It's okay to fail, it's okay to suck. I play piano and I'm just like, I'm not good, I'm gonna sit. And like, that's fine.
Learning to do things that for you are helpful and positive.
Yes.
Learning how to breathe, the thing that we do all the time. Right.
Yeah, we're from roughly the same cultures, the same area of the world, so we might dance a little bit while we're on screen, so just bear with us. Do you want to give us like the one-line premise? Because I feel like it's over-practiced now.
No, well, no, it's just like I have come up with the solution to all the world's problems, right? Climate, of course. We've eradicated global poverty, have true trans-species democracy.
Yes.
And we just had to turn back technology a little bit, and everybody has to leave by 50.